So about the partial properties, and then what else? I think it's on the properties what is it? Ideal gas mixture lah. Mostly on the property change of mixings, right? And how to determine the Fugger. So you will do the tutorials on the how to determine the fugacity of the pure liquid, as well as the fugacity. Yeah, fugacity. You have to determine the fugacity coefficient first, and you have to determine the after you determine the fugacity coefficients, you can determine the fugacity lah. And also the fugacity coefficient of the species in the solution. Okay, that's the important one, because once you deal with the binary mixture or more than two phases or two mixture, so you have to determine the fugacity of the species for each species in the solution, whether in the gas phase or the liquid phase. Okay, so for today's I think about the partial properties. Okay, about the partial properties. Um, Actually, is partial properties is for example, is like if you familiar with the partial pressure, that one is of the one of the partial properties lah. Okay. So based on definition of the mu n, okay. So if we defines the partial molar property as here lah, okay. So this one is in generals, the question general equations, okay. M bar, it should be have a bar here, okay, and partial, there's a partial differentiate lah, okay. That's why we call it a partial differential, partial properties, okay. M and also Ni. This is a Ni is a number of mole of species. Okay. So M can be V, U, H, S, and also G. Okay. So this is the partial properties of the individual species because Ni, right, exists in the solution or mixture. Okay. So you have to remember that the properties is different with the pure species. Okay, because of once you mix, okay, the partial properties is going to be the properties is going to be different because once you mix, there's going to be interaction. Okay, especially at high pressure or temperature, interaction intermolecular, maybe attraction and what is it, attraction, uh, re- apa lagi, tarik dan tolak. Apa saya lupa lagi satu dia punya the term. Okay. uh, Attraction and repulsion. Okay, sorry, attraction and repulsions, okay, is become significant at high pressure and also high temperature. Okay, sorry. Yeah, attraction and repulsion. Okay, so that's why the properties is different once you mix. This is the reason why we have to determine also one of the what is it, what we call it, chemical thermodynamics that related with uh, uh, the real gas. Okay. Once we this at the vapor phase, okay, you have to determine the fugacity lah. Okay, what's the definition of fugacity later? I will ask you. Okay, what do you understand about the fugacity? Okay. Okay. If you look at here, that the chemical potential of species I is known also as partial properties of Gibbs energy lah, for the species I. Okay, it's similar. It's chemical potential, right? So the tendency of the, for example, like species try to escape from the liquid phase to the gas phase. That is the one of the chemical potential lah. Okay, like a previous example, right? The chemical potential at 0 degree C for the ice cube and the water, right? More than 0 degree C and below than 0 degree C, right? Okay, it's related with the chemical potential. So partial get on partial. This is the what we call it as a partial Gibbs energy lah. Okay, partial property of Gibbs energy. Okay, so generally for the relationship of the molar and partial molar properties, okay, for the pure species properties, Mi, this one is pure species properties, right? This one is a partial properties. M is the solutions. Okay. Uh, if you look at here that this is I lah, there's a no bar here. This one is a partial, okay, and this one is for the solution of the mixture properties. So you have to remember this, these symbols. Okay. U is for the internal enthalpy, entropy, and also Gibbs energy. Just the difference is they have I, or they have a bar, or just without I. Is a I is represent the species of that particular species. Okay. So this is the derivation. Actually, I have some other slide. I think you download. You have this slide. Right? I just skip. This one is just the equation that related with the molar and partial properties. So it's a derivation. Okay. For you, you just apply the equations. Okay. So for this one, if you look at here, yeah. For the enthalpy, okay, Hi bar equal to Ui bar plus PV bar. This one of the, this one is for solution, this one is bar. Okay. Okay. So equation for the constant compositions, if you look at here, H equal to U plus PV. Similarly also for dG equal to VdP minus S dP. This is a fundamental properties of relations, right? Okay, and when you convert to when you write in the partial properties, so it's going to be have a bar. Okay, so this is the application also partial properties. So actually at the ideal gas state, okay, the partial properties of the enthalpy or what else, internal energy is going to be similar with the Hij lah. So meaning that it's gonna be the same lah. Okay. Because Hij is equal to summation of Yi Hij, right, for each species. Okay. So generally for the property change of mixing, so for the enthalpy is gonna be 0. Okay, so that's what you have to know. Later I will explain. Okay, so let's see the ideal gas mixture. Okay. So for ideal gas mixture, if you remember, right, this one, right, for example, right, this one, right. So if you have a number of mole and moles of the ideal gas mixture, okay, that occupy the total volume VT lah, right, VT, at the temperature, and then you can, if you still remember that, alamak, this one, right. Sorry, yeah, wait. PV equal to nRT, right? So PVT, this is total volume. So once you rearrange, you can get this one lah. Okay, once you rearrange. So this one is partial. This is partial. This one. Okay. So P is equal to nRT divided by VT. Okay. Similarly, also for the pressure that species I. Okay. Exert if alone occupied at the total molar at the molar volume of the mixture. So it's gonna be PI lah, partial pressure of that species. Okay, because in the solution, right? Okay, and this one is for the gas mixture. So if you divide for both, so you can get this expression. So meaning that PI is equal to YIP lah. This one. So this is the partial pressure lah. Okay, if we divide. Okay. So Yi is the mole fraction of the species I in the ideal gas mixture, and also this one is the partial pressure of the species I in the solution. Okay. So in order to get the total pressure, you have to sum of the partial pressure. Okay, for example, you have species A, B, C, right? PA plus PB plus PC, right? So you can get P total. This is the you already learned in the what is it? In the mass and energy balance class. Okay. Okay. So how about the volumes, right? Okay. So molar volumes, if you look at here that you have system A, B, and also C. Okay, for species 1, 2, that one is for B lah. And the mixture C, 1 and 2, right? For this one. Okay. So with the expression similarly with the partial pressure, partial properties, if you still remember in the previous slide, this one, right? Okay, so you can express the equation in term of the you can replace this one lah with the volume partial volume side, so you can get this expression. So equal to, so just replace with the VIG, right, with nRT, so you can get this equation. Actually is a similar VIG and VIG VIC is a similar. Okay, so meaning that the partial molar volume is identical with the pure species volumes at the mixture of temperature at the same temperature and also pressure. Okay, this is only applicable for the molar volumes. Okay, it's only for molar volumes. But for other thermodynamic properties, it should be measured in the partial pressure. Okay, so from this one, okay. So from this one, we can define based on the Gibbs theorem. Okay, a partial molar properties other than volumes. So you look at here, right? Other than volume of the constituent species in ideal gas mixture is equal to corresponding molar properties of the species as a pure ideal gas at the mixture, but at the partial at the pressure equal to its partial pressure. Okay, so meaning that this MIG is not the same with the VIG lah. This one is similar. VIG, the partial molar volume is equal to molar volumes for the ideal gas lah. Okay, but this one is for U, H. Okay, it should be at the partial pressure. Okay, partial pressure of the mixture. Okay, for example, this one U lah, this one U. Okay, for the species I. Okay, at the partial pressure. Okay. So if you look at here that for the partial molar HU, CP, and also species I, for the since enthalpy is the independent of the pressure. Okay, so for the species I, HIG, we can see that partial pressure of HIG equal to HIG lah. Okay, similarly also for internals. So for ideal gas mixture, so because this is a derivation of the from for the property change of the mixing. Okay, y is equal to 0, right? Okay, so since h bar equal to hij, okay, so this one is equal to summation of yi hij lah. Okay, so it's similar, so you can get this one. So this one you bring to the left side, so you can get this equation, right? Okay, so you can get this equation. Okay, so once you get these equations, okay, this is the properties change of mixing. This is actually properties change of mixing. This one you can do lah also for the internal energy and also CP. This is the property change of mixing, meaning that delta H I Ig mix equal to 0. Okay. So for the ideal gas, okay, the enthalpy change of the mixing is equal to 0. You have to remember that because it's independent of the pressure. Okay, except for the entropy. Okay, entropy and in parallel with the Gibbs energy. Okay, so entropy is depending on the pressure. Okay, so it's not equal to 0. For other thermodynamic properties and what is it? Property change of the mixing is equal to 0. Okay, so you have to remember that. So if you look at here that for enthalpy, property change of the enthalpy and what is it? internal energy as well as, what is it, another one? I cannot see that up here. Delta Vig is equal to 0. Okay. So delta Mig mix equal to M final minus M initials. Okay. So it's similar lah this one. Like just now Hig, right? Minus summation Yi Hig. Okay. So equal to 0. Okay. Enthalpy change. This is from the derivation in the previous for the ideal gas mixture. Okay, because initial and final condition is going to be similar. It's independent of pressure. Okay, but for the entropy is dependent on the pressure. Okay, so this is you have to remember. Okay, so for the entropy change of mixings, uh, okay, so you have to use this equation from the chapter 6, right? So once you rearrange, you can get this equation. Okay, Sij. But if you this one change, right? This one is going to be the same. Okay, this one, right? So once you replace this one with YISIJ and bring it to the left side, so you can get this one, right? This one, bring it to the side, so you can get delta S. Change in the properties lah, entropy change of the mixing Sij and mix. So you can get this equation. Okay, you can write in terms of this equation or this equation. Okay, because there is a negative here, right? Because there is a negative, so you can 1 divided by yi. So if only y is going to be negative here, right? So in parallel also you can so you look at here, that must be positive, okay? So it should be to see the spontaneous of the this one, where the erection or the phase move forward. Okay. So in parallel also we can express in terms of Gibbs energy. Okay. This one. Since the chemical potential is the partial Gibbs energy, so we can write in term of GIG. So plus RT non 1. Okay. So we can write also another alternative expressions here, this one. This one. But this one is an integration constants. Okay. Generally we use this one, this equation. Okay. So we can get, finally we can get data gives energy, okay, of the ideal gas mixture. Okay, property change of the mixing for the gives energy, so we can get this one. Okay, so G by G. Okay, so in summary, since independent of pressure, this one U, so actually if property change of mixing is equal to 0 lah. Okay, if you bring it to the left side, this one, right, so equal to 0. And dependent of pressure, SIG and also Gibbs energy. Okay, this is Gibbs energy. Okay. So finally, for the property change of mixing, so you have to remember this one. Okay, delta HIG, delta UMNG, VIG equal to 0. And this one is dependent of the pressure. Okay, so you have to highlight this equation for the property change of mixing. Why we deal of mixing? Because they have many species. And also now we are deal with more than two but generally it's just a binary lah for now. Okay, the binary system. If more than two component is gonna be more lah. Okay, maybe tertiary or quaternary, right? But now we are focusing on the binary. Okay, any questions? Okay, so let's we do this example too. Okay, for the example too, what is the entropy? What is the entropy? What is the change entropy when 0.7 cubic meter of CO2 and 0.3 cubic meter of nitrogen, each at 1 bar and 25 degrees C, blend to form a gas mixture at the same condition? Assume ideal gas. Okay, so the equation that you have to use this one. Okay, this one. This one. Can you calculate? Okay, starting from next week's, I will conduct the class physically. Okay, since nobody respond on me that you are what is it? Everybody is already in UTM, right? Okay, so I guess we can start the physical class face to face next week. So please check the schedule. Okay. On Sunday, I think room is N0128. Okay, N01. Not N01. Okay, 28 lah. Okay, 28. The room number is 28, I think. N028. 28. And then on Tuesday is 210. Okay, N02. N02. Okay, N02. Okay. So I will conduct physically next week. Starting from next week, Sunday. Okay, please remember 4 to 5, and also this one is the 11 to 1 o'clock. Okay, boleh tak next
Doctor,
week? Huh?
just now we also got class lah. Like today, I think we will be late for the class lah. Go to the class.
Apa dia?
I think we will
Okay.
be late.
Kelas apa?
Tadi electrical technology lah.
Biasanya kita tak akan habis, sepatutnya kelas tu habis 10 minute before. For example, our class is 11 o'clock, right? They should stop at 10:50. Okay, that is from the academic circular. Okay.
Oh,
Faham eh?
okay.
Dia tak ada, there's a no exactly sharp it finish 11 o'clock or 10 o'clock. It should be 10 minutes before, um, just now like 11 o'clock, 10 minutes before the this one end of the class. Okay. Tapi tak tahu lah, lecturer biasa dia akan lebih. Okay. Sepatutnya dia kena tahu memang perkeliling tu 10 minutes. Okay. Before contohnya 11 o'clock, right? You have to stop 10 minutes before 10 o'clock. So you have to stop. Okay. Even for, yelah, sebab selepas tu dia akan ada kelas lain guna bilik tu kan. So they have to get prepared also. Okay. So saya for me I just maybe I will start after ni lah 5 minutes. Okay. 5 minutes or 10 minutes. Okay. Okay. Please do this example too. If you look at here, that this one is an ideal gas, right? So just assume that the what we call it as this one, what cubic meter, uh, volume fraction. Okay, this is the volume fraction is equal to same as the mole fractions. Okay, so meaning that once you add both this molar fraction volume fraction, so you can get equal to total is equal to 1 cubic meter because it's ideal. So when you add, it's going to be exact number. Okay, it's not going to be reduced. Okay, so if you look at here, please calculate the fractions. Okay, so uh, this one. Okay, pressure 1 bar. T equal to 25 degrees C. Okay. Yi, Y2. What is the fraction? Okay. So from the equations, delta S, what do we have? Entropy, change of entropy like S Ig mix equal to negative NR. Okay. Summation Yi on 1. Okay. So if you look at here, there's a number of mole. Okay. So please calculate number of mole. Ei divided by RT is determine number of mole. Okay. Mole. So delta S equal to just substitute into this equation. So please calculate. Give me the value. I give you 5 minutes. Okay, give me the answer. What is the number of moles as well as the delta S mixing? Give me the value. Irene.
The number of mole I get is 40.3418 mole.
Okay. 40.31. So please calculate the delta S mixing.
And the delta S is 204.8849.
Okay, Joule Kelvin. Okay, thank you. Okay, example 3. Can you do? Please proceed with example 3. Okay, if you look at here, that the nitrogen flow at 2 kilogram per second and hydrogen at 0.5 kilogram per second. Okay, mix adiabatically. Okay, in steady flow process. What is the rate of entropy increase as a result of the process? So if you look at here that it is given in terms of 2 kilogram mass flow. So you have to convert to the molar flow. Okay, molar flow, and then you can convert to mole fractions lah. Please convert to the molar flow and then change it to the mole fractions, and then after that you can calculate the delta S. Okay. Okay, anyone? So how to calculate the molar flow? This one is a mass flow, is from this data is a mass flow. How much the value you can get for the fraction? So how to get the molar flow? Anyone? This one is mass flow. Nurul Ain, what is the formula to get the molar flow? Nurul Ain Azhar. Are you there? So if you look at here that m dot, what is it, nitrogen, right? Equal to 2 kilogram per second. Then m dot hydrogen equal to 0. Yes, divide by molecular weight. Thank you, Nurul. Kilogram per second. Okay, molar flow. Molar flow, what is the symbol I want to use? N lah. Okay. N tu. Okay. So N2 divided by molecular weight N2. So you can get. Similarly, also you do for hydrogen. Okay. So from this one, you have to get the NT lah. Because you want to calculate the fractions, right? Molar fractions. So Y1 lah. Just nitrogen is Y1. So and nitrogen divided by and T. Okay, so you can get Y1, Y2, H2. Oh no. Just calculate. So once you get the fraction, so delta S Ig mix equal to negative R and T, right? Summation Yi known Yi. Okay, calculate. Okay. Want to see. Li Wan Yi. Done. Calculate. Li Wan Yi. Calculating. yn2 0 point yn2 0.223 y 0.7. Okay, okay, thank you. So please proceed, calculate the calculation for delta S. What you get? One four one seven. Okay, 1417. Okay. What's the unit? What is the unit? Okay, joule per second and Kelvin. Okay, thank you. Okay, so I hope everybody can get the similar or almost similar answer. So even for my answer is one. Is there any negative? Please check whether there is a negative or not. 1412.56 joule per second Kelvin. Okay. So let's we move to the next part. This is about the fugacity lah. Okay. Okay. So for this part, we will discuss on the fugacity and fugacity coefficient for the pure species before we move to the species in solution. Okay. For the species in solutions, I mostly we deal with the binary system. Okay. Because of more than the binary, I think it's quite difficult. Okay. And if you want to uh, how to say if you're interested to study more than two components, okay, so you can refer to the any engineering thermodynamics books or chemical engineering thermodynamics books, okay, or you can refer to this book, okay, there's a advanced thermodynamics. Okay, so okay, for this one, the scope of lecture is going to be fugacity and fugacity coefficient for the pure species. How to calculate the fugacity coefficients, especially before we determine the fugacity, by using virial. I think it's mostly virials as well as generalized correlations. Okay, Lee, Kessler, and as well as mu phi equal to phi, and yeah, that one is Lee, Kessler. Okay, and also virial. Okay. And then species in solution, ideal solution, and also non-ideal solutions, and also the calculation of fugacity for the pure liquid. Okay, it's going to be different. we're gonna use a Poynting factor for the calculation for the liquid. Okay, you can use the for the gas phase, but I think it's not really accurate. Okay, for the pure liquid is we can consider as a compressed liquid. Okay. Okay, so this is a definition of the fugacity. Okay, in terms of the adjusted pressure. Okay, so the unit is gonna be similar whether you want to use ATM, PSIA, or bus and etc. Okay, so what you can understand is when you deal with the chemical potential of the component in the gas phase. Okay, all the components that may be in the gas phase. Okay, so we can use this fugacity lah, because if you look at here that it's reflect the tendency of the substance to prefer one phase. Okay, solid, liquid and gas. It's try to escape from another phase to another, from one phase to another phase lah. Okay, so we can literally define as the tendency to flee or escape. This is the definition of the fugacity. Okay. Okay. So generally we want to know the difference between the chemical potential of the interest, especially in maybe at the gas phase. Okay, the interest lah, mu I. Okay, and the chemical potential of the pure substance at the temperature, at a particular temperature, and also the pressure is 1 bar lah. Okay, so the phase with the lowest fugacity will be the most favorable and will have the lower Gibbs free energy. Okay, so if you want generally chemical potential is a move from the higher chemical potential to the lower chemical potentials. Okay. So for example, what is it from the liquid to the gas, right? So we can measure the tendency of the component, okay, of the liquid mixture to escape, right? Because the tendency to flee or escape or vaporize from the mixture, okay, to the gas phase. Okay, that's the what we can understand about the fugacity. Why you have to determine the fugacity? Okay, because we did not deal with the ideal gas. Okay, we deal with the real gas. Okay, fugacity is for the gas phase lah or vapor. Okay, so how to determine the fugacity? And before we determine the fugacity, we have to determine the fugacity coefficient lah. So first thing we have to use for the pure species, we use a cubic equation of state. VLE for pure species and also pure liquid species, and solution is mostly we use the variance lah, fundamental relation, property relation, and also variance. Okay, and then the last correction for the phi. This one is the fugacity coefficient. Phi is the fugacity coefficient, right? Extension of the mixture. And the rest is excess properties and also ideal solution model. For ideal solution, we use the Lewis Randall rule. Okay. Okay. Let's see for the pure species. If you still remember from the previous slide about the concept of the Gibbs energy for the ideal gas, we use the pressure, right, to the real fluids. We want to apply the equation similar to the this one, right? GIG tau I, okay, RT ln P, right? This is for ideal gas, but we want to apply for the real fluids. Okay, so we have to replace this P with the fugacity. This one, fugacity of the pure species. We call it a pseudo pressure. Okay, because it's approximately, okay, close to the value of the pressure. Okay, pseudo pressure. Okay. For a gas under ideal gas condition, you have to remember that fugacity is going for the species is similar with the pressure. Okay, because it's ideals. Previously we deal with the ideal, right? That's why we use pressure. But reals we use fugacity. Okay, so remember that. So how to calculate the fugacity? Okay, based on the equation of what is it? Real Gibbs energy for the species, and also Gibbs energy for the species at the ideal gas conditions. Okay, so we just subtract lah. Okay, if you look at here, Gi minus Gig, right? So we can get residual, right? This one. So we can get this expression. So this is a fugacity and also P. How to determine from this one is phi I equal to fi P lah, because phi I is equal to this one. Okay. Fugacity coefficient. Okay. So in order to determine fugacity for the pure species fi pi p. Okay. So this is a dimensionless quantity. Okay. So for ideal gas, there's a no residual Gibbs energy. Okay, is equal to 0. So phi I equal to 0. Okay. So our concern is how to determine this phi I or fugacity coefficient. Okay, because in order to determine fugacity, you have to determine the fugacity coefficient. Okay. So this is we just make it phi I lah. Okay. That one. Okay. This is a phi I. Dimensionless quantity. Okay. So how can we determine this phi fugacity coefficient? Okay. Okay. So if you still remember, right, in chapter 6 about how to determine the Gibbs energy, what else? Enthalpy and also entropy, right? Residual Gibbs energy, right? Okay. If you still remember this equation, GR for RT, although P 0 Z plus 1 dpp. This one that we have to determine by using a graphical method, right? So if you rearrange, okay, and substitute with the fugacity coefficients, kenapa saya punya cursor ni asyik hilang je kalau saya buat full screen? Salah tu. Okay, right. If you still remember that equation, right? Okay, if you rearrange, right, so you can get this expression from chapter 6, this one. And also in terms of residual Gibbs energy. So we can get this equation, right? To determine one of the method is to determine is by using graphical method. Okay, by using a graphical method. But this is a how to say, a tedious method lah. So a tedious step to determine the fugacity coefficient. So how can we determine is one of the method? For example, it could be equation of state and also what else? Virial equation. So it's depending on the pressure. Okay. So from the virial coefficients, if you look at here that for the pure species, BII is equal to pure species lah, equal to B. So this is a unit, this constant, right, from the any handbooks. Okay, this is 2 terms, meaning that from low to moderate pressure. Okay, you cannot simply use for the high pressure. Okay, so we just replace this one, right? Z minus 1 with BP over RT. So substitute into this equation, so you can get this equation. So the problem is on B, how to determine the B. Not all the components have this constant and different pressure. Okay. So what we have to do for the alternative equations, we can use by using what we call it as if you still remember that general correlations, right? So we substitute with B naught plus omega B prime. Okay. So just use that equations and substitute. So you can calculate fugacity coefficients. B0 and B1 is already provided. So just substitute TR and substitute into this equation, so you can calculate fugacity coefficient. Okay. So 2 term virials, low to moderate pressure. Okay. This is one method. Okay. And for the cubic equation of state, okay, so this is the equations. Okay. The one cubic equation of state that we not cover is only for the species and solution. But for the species, yes, we cover cubic by using cubic equation of state. Okay. So how to calculate this one? Non phi. You have to determine Zi. How to determine Zi? So refer back 349. This is iteration, right? Bi also, Qi and II. So generally we use this one, right? Epsilon not similar with the gamma. Okay. This one is only for van der Waals. Okay. So you have to determine and substitution so you can get the coefficient. Okay. Once you determine Fi equal to Ai. So please remember this one is only for pure species. Pure species, okay? Not species in solution. Species on solution is for the mixture. This one is for the pure. Okay? Okay. So the third one, okay, first virials, okay, second is cubic, and the third one is for the generalized correlations. Okay, this is a Lee Kessler. Okay. So how to determine this one? You have to refer to the appendix to determine phi naught and phi prime. So you need omega. So you can get. So this is interpolation. Interpolation or extrapolation. So extrapolation. Okay. So similar. Please remember video, cubic question of state, and then generalize. This one is Kessler. Actually, if this one is a generalized also, right? Is a generalized. Okay, but in alternative question because this one is not all the component we can value for B. Okay, if in equilibrium you have to remember that fugacity is similar for each phase. Okay, fugacity in the vapor is similar with the FIL. Okay, vapor and liquid. Okay, this is in equilibrium, okay, equal to Fi saturated. Similarly, also fugacity coefficient. Okay, for the pure species, coexisting liquid and vapor phase are in equilibrium when they have the same temperature, pressure, and also fugacity. Okay, you have to remember that one. Okay, and that one is for the vapor or for the gas. How about for the liquid? Okay, we use the Poynting factor. If we consider that the pure liquid is a compressed liquid, right? So we use the Poynting factor equations. This is just derivation. So you use this one, okay? Please highlight this one. So you need Pi saturated, and Pi saturated will be liquid lah. Okay, this is fugacity for the pure liquid. Okay. So you need this one for the liquid. Please remember, the previous one is for the vapor. This one is for liquid. Okay. So what I would like to remind you for the vapor and vapor. Okay, how to determine? You have to determine the ion vapor, right? So and then this one is virial, right? And then cubic equation of state and generalized correlation. Okay. So for the liquid FL, this one just Poynting factor. Poynting or Poynting. How about the Poynting? Alamak, hilang pula kerja saya. Disappear. So just a Poynting factor lah. This one. Okay. POY. POY and TING. Okay, Poynting factor. Okay, let's do the tutorial before we stop. This is a last tutorial. For SO2, example form, at 300 bar, determine the good estimate of the fugacity and of the R divided by RT. Okay, so if you look at here, that 300 bar and 600 Kelvin, which method that we can use? Which method? Anyone? Tan Li Ting. Which method you can use? Tan Tan Liting, are you there? Tan Liting.
Yes, doctor.
Which method that we can use? For SO2 at 600 Kelvin and 300 bar, determine the good estimate of the fugacity and GR over RT. Which method to determine the fugacity? Huh? I cannot hear.
Lee-Kessler correlation.
Okay. So since this is a high pressure, so you can use a Lee Kessler. Okay. So if you look at here that what you have to do is temperature 600, 300 for the pressure. So please determine TC. TC and also omega. Please determine. And then TR. TR. Please determine. So please refer to the table E lah, appendix. Okay, E15 to E16. Okay. So by using phi equal to P naught, right? P prime omega. So ln P equal to ln P naught. P prime. Okay. So once you determine ln phi, phi lah. Okay. F equal to P. Right. So you can get F lah. Please calculate. And then GR over RT equal to ln phi. So please determine GR. Okay. Let's determine. Give me the answer. Oh, yeah. What is TR and PR? Give me.
value of TR is 0.6964. The value of PR is 7.6104.
What is it? TR?
TR is 0.6964.
Are you sure? 0.9.
6964.
0.6964. How about this one, PR?
7.6104. 6.
104. Can you check? Is it correct? What is TC? For you? TC.
TC is 430.8.
Okay, 430.8. 600 divided by 430.8. 1.353. How come you can get more than that?
Oh, sorry, doctor.
T divided by TC, okay? Or you do TC divided by T.
I wrote 300. I careless mistake.
So your answer is going to be 1.353. And this one 3.805. Okay. And please determine phi naught and phi prime. Okay, so what's the value phi naught and phi prime? So omega is 0.5. Ikram Nurazam. What is the phi naught? This one, value and phi prime. Really? Let's see. 0.724. Teo Chong Seng, what is it? 0.724. 0.7134. Okay, so that is correct. Okay, Teo Chong Seng. And then F. Okay, total fee. Okay, fee. Fee. Okay, PHI. Not fee. Fee. PHI. Pi. We call it phi or fee. I don't know. Pi or fee. Pi, I think. Call it pi, right? 0.7. Okay, thank you. Teo Chong Seng. How about Fugasti? This one, we call it fee or pi? PHI. Can you, anyone know? Hmm. So this one is 0.724. Okay, thank you. 217. 217.15 bar. And the rest you can calculate. Residual. Residual is a negative 0.323. Okay, so that is the answer. Okay, so can you calculate this one? Fugasti at 20 bar? This one. Which method that you can use? Anyone? Which method? Muhammad Izzat? Siapa tadi saya sebut nama? Saya lupa pula. Ikram. Ikram Nur. Are you there? Ikram Nur. Ikram? Ikram tak ada? We can use video because okay. So please calculate. Ikram. So by using reals. Okay. So you can use this method. 20 bar. This one. Because it's just 20, so we can consider as moderate. Not low. We can consider, we can assume that 20 bar is a moderate. Okay. So please calculate. So what you have to do is determine TC, TC, TR, TR. Okay. What else? Variables, of course. Once you determine this one, right? Omega. And then phi. Total. Is it exponent? exponent PR divided by TR. Okay. B naught plus omega B prime. Okay, this one. So fugacity exponent PR divided by TR. B naught plus omega B prime. Jarak dengan P lah. Okay. So you can get please determine B naught B prime. So give me TR, PR, B prime, B naught. Aplikasi dia. Give me B naught and B prime. Aplikasi dia. B naught and B prime value.
Setiap data tengah kira.
B00 0.18. Okay, so that one is from Hafika Sidin. Thank you. So please calculate the fugacity. Pressure, you know, right? So if you calculate and substitute, this one is 0, 8, 1, 8, 6, 4, 6, 4, 6. And this one is 0.0860. Fee 0.97 fee. I'm not sure about the fee. Okay, but you can calculate directly because this one I just directly calculate the fugacity lah. Just substitute this one. So this one you can get 18.76 bar. Yep. Okay. So Tan Li Ting's give the value for fee. So I think it's correct. So for me, I just calculate directly to determine fugacity. Okay. Okay. So estimate for tutorial 2, estimate the fugacity cycle pentane 110 degrees C and 275 at 100 degrees the vapor pressure of scavenger is 5267. Okay. If you look at here that how to calculate this fugacity. Okay. Okay. So you look at this one. Okay. Please solve it. Okay. I will ask you for in the next class. Okay. Whether you want to use, if you look at here that whether it's a liquid phase or gas phase, you have to determine. Okay. How to determine if a liquid, you have to use this equation. So how to determine this VI liquid at the saturated point? Okay, PI saturated and PI saturated. Okay. So for PI saturated, if you look at here that the pressure is 5267 bar, right? Okay. So you have to determine at that condition. Okay. So please do this one and I will ask in the next class. Okay, any questions about how to calculate the fugacity and fugacity coefficient? Okay, so I guess no questions. Do not forget that our test, okay, on 12, okay, at night. So it's going to be online, open book. Okay, maybe test 2 is going to be physically. Okay, so that's all. Thank you very much. Please do this tutorial too, and I will ask the answer in the next class. Thank you very much. That's all.